You lift your eyes toward the night sky, and for a moment you imagine you are seeing the universe as it truly is, a clean snapshot of what exists right now. But you are not. Almost nothing you see is still there the way you see it. Every point of light above you is a message from the past, a signal that has been on the road for years, centuries, even billions of years before it reaches you tonight. You are not looking at the universe as it is. You are looking at its delayed broadcast, at ghosts made of light. Some of those ghosts are close. When you see the moon, you see it as it was a heartbeat ago. When you look at the sun, you see it as it was 8 minutes ago. A nearby star might be showing you its face from before you were born. The deeper you look, the more extreme that delay becomes. There are galaxies whose light began its journey when no cities existed on Earth, and others whose light left home before Earth existed at all. Some of the light now reaching you started moving when the universe itself was only a few 100,000 years old, wrapped in its first faint glow. Now add one more fact, the one that quietly changes everything. While that light has been crossing the dark, space itself has been stretching. The universe is expanding, and it is not slowing down. The more distant a galaxy is, the faster it recedes from you. Some are now being carried away so quickly that no new light from them will ever reach you. Not in 10 billion years, not in a trillion. They are not just far. They are gone, locked behind a boundary that no signal can cross. That means most of the universe is already lost from view. Not because it vanished, but because space itself is dragging it away faster than light can keep up. You live inside a limited bubble of visibility, a region of space about 92 billion light years across, and everything you will ever see is contained inside that bubble. Beyond its edge, the universe keeps going, but its stories will never arrive. This is the part that grips you when you let it sink in. You are sitting here, maybe at the end of a long day, with a phone or a laptop in your hands, and the universe above you is a compromise between what is real and what is reachable. The title that brought you here asks, what lies on the other side of the universe? And the first honest answer is this: almost everything. Almost everything that exists is already beyond the reach of any light that will ever touch you. So the question becomes sharper. If you could somehow walk to the very edge of what you can see, if you could stand at the outermost shell of your observable universe, what would you find there? Would there be a wall, a border, a final curtain? Or would you discover that the edge is not a place at all, but a limit built into reality itself? Astronomers call that limit the cosmic horizon. It is not made of matter or energy. It is made of time. Anything whose light has not had enough time to reach you is, by definition, on the other side. It might be perfectly ordinary out there. Stars, planets, clusters of galaxies, maybe even life. But from your point of view, it is sealed away forever, as unreachable as yesterday. Imagine standing on the shore of a dark ocean with a narrow beam of light in your hand. No matter how powerful it is, its circle only reaches so far. Beyond its edge, the waves still roll, the water still moves, but you never see their shapes. The universe is like that, except the beam is not your flashlight. It is the speed of light itself. Your entire cosmic experience is confined to the circle that beam can cover in the age of the universe. You, living now, are in a short, privileged era. You can still see far. You can still detect the afterglow of the Big Bang as a faint microwave hiss. You can still map distant galaxies and watch them fly away. Tonight, you are going to follow those clues outward. You will drift, in your mind, past the familiar constellations, past the thick disk of the Milky Way, past the clusters where galaxies swarm like fireflies in a jar, until the galaxies thin and fade and the light grows older and redder. You will stand, as much as a human mind can, at the edge of what light can show you. And then you will keep going, not in miles or meters, but in ideas. You will explore what it means for the universe to have a horizon. You will ask whether space goes on forever, whether there are other cosmic bubbles beyond your own, whether reality might be larger and stranger than anything your eyes can ever directly witness. By the time you return from that journey, you will understand why the universe has an edge you can never cross, why most of what exists will forever lie beyond your sight, and why that limitation is not a failure of your instruments, but a fundamental feature of the cosmos. For now, you do not have to solve any of that. You only have to lie back, breathe slowly, and let your thoughts drift outward. The universe is vast. Your life is small. But somehow, in this moment, the two are touching. You are about to walk, in your mind, to the border between the knowable and the unknowable, to the place where the last real galaxies fade into pure possibility. And it all begins with understanding the horizon itself. When you think about the universe stretching in every direction, it's easy to imagine it as something open and endless, a vast ocean without borders. But the truth, the simple, elegant truth, is that you live inside a sphere with a measurable radius. Not a sphere of matter, nor a sphere built by walls or gravity, but a sphere defined entirely by time. This sphere is called the cosmic horizon, and it marks the outer limit of everything you can ever see. To understand it, you start with the most basic fact in all of astronomy. Light has a speed, and that speed is finite. No matter how bright a star is, or how violent a galaxy becomes, its light still travels at the same universal limit. That means when you look far away, you are also looking far back in time. If something is a billion light years away, you see it as it was a billion years ago. If it's 10 billion light years away, you see it as it was 10 billion years ago. There's no shortcut. Every distant object is a window into the past. But here's the part that bends your mind. The universe is 13.8 billion years old. So you might think the farthest thing you could possibly see is 13.8 billion light years away. Yet the actual radius of your observable universe is about 46 billion light years. That's because while the light has been traveling toward you, space itself has been expanding underneath it. Imagine running towards someone on a moving walkway that's rolling backward. Even if you run at full speed, the ground stretches between you. The same thing is happening to light from the early universe. It has been traveling toward you for 13.8 billion years. But the space it crossed has expanded so dramatically that it now lies tens of billions of light years away. So the cosmic horizon is not simply a distance. It is the distance that light has been able to travel since the beginning of time, stretched by an expanding universe. You live inside that boundary, like a person standing at the center of an enormous sphere. Everything inside is visible, at least in principle. Everything outside is hidden forever. It isn't that those regions don't exist. They do. They're full of galaxies, stars, planets, and structures as real as anything you can see. But the light from those regions has not had enough time to reach you, and because space is still expanding, it never will. You live inside a bubble of ancient light. Every photon inside this bubble has fought its way across cosmic distances, through expanding space, across billions of years, just to brush your eyes. And every photon outside this bubble is forever out of reach, sealed away by the simple fact that time has not allowed it to arrive. If you picture this bubble, picture it carefully. You are not on its surface. You are at the center. Every observer, no matter where they are, also sees themselves at the center of their own sphere. That's because the horizon is defined not by location, but by time. You are standing in the middle of a sphere of time. A sphere whose radius is the age of the universe multiplied by the stretching of space. A sphere whose surface is not a place, but a moment. The moment when the oldest light you can possibly receive finally reaches you. Because the horizon is defined by time, it is not fixed. As the universe ages, the horizon grows. New regions of space drift into view, not because they are moving closer, but because their light finally has enough time to reach you. But at the same time, because the expansion of space is accelerating, other regions drift away faster than light and slip permanently beyond reach. The horizon moves like a shifting shoreline. It advances in some places and retreats in others. It changes the universe you are able to witness without warning or sound. This is why the cosmic horizon is not the edge of the universe. The universe may be infinite. It may be curved. It may be shaped in ways you cannot imagine. The horizon is simply the boundary between the part of reality that has delivered its light to you and the part that hasn't. There is no wall out there, no edge, no cliff, just a limit made of time. A limit imposed by the finite speed of light and the stretching of space. When you look toward the horizon, the galaxies you see are not behaving like the galaxies nearby. Their light is older. Their colors are stretched into deep reds. Their shapes are blurred by distance and time. They look frozen, caught in ancient poses, unable to reveal what happened next. They are not frozen because they stopped moving. They are frozen because their future light will never reach you. You see their deep past, but you will never see their present. Somewhere beyond that faint boundary, galaxies are colliding, forming, and dying at this very moment. Stars are being born. Planets are pulling themselves together out of dust. Structures on unimaginable scales are rising and dissolving. But those stories are lost to you, not because they are unimportant, but because the horizon keeps them hidden, wrapped in silence. You cannot hear them. You cannot see them. They live on the far side of time. As you sit here tonight, letting your breath slow and your thoughts drift outward, the horizon becomes more than just a measurement. It becomes the first wall, the first limit that defines your relationship to the universe. Understanding this wall prepares you for the deeper ones that follow. Walls shaped by the earliest moments of creation, by the breakup of space-time, by the wild possibilities of other universes, and by the ultimate structure of reality itself. Alan Guth once said, "Inflation explains why our universe looks the same everywhere we look." That idea will guide you next. Because if the universe has a horizon, it must have had a beginning. And that beginning was faster than light. To understand why your universe has a horizon at all, you have to step back into a moment so brief it almost doesn't seem real. A moment so fast, so violent, and so transformative that every galaxy, every star, every atom you will ever see was shaped by what happened in a fraction of a second. This moment is called inflation, and it was the first time the universe outran light itself. When you hear the word expansion, you might picture galaxies rushing away from one another, like shrapnel after an explosion. But that isn't what happened. Inflation wasn't things moving. It was space stretching underneath everything. Imagine the fabric of the universe pulling itself apart so quickly that distances doubled, not in millions of years, not in centuries, not even in seconds, but in an instant so tiny you can barely comprehend it. 10 to the minus 32 seconds. A decimal point, followed by 31 zeros, and then a 1. In that unimaginably short blink, the universe went from smaller than an atom to something macroscopic, large enough to lay the foundations for every structure that would ever exist. You can picture it in your mind as a kind of cosmic unfolding, a sudden stretching of the invisible grid that defines space itself. One moment the universe was compressed, quantum-sized, filled with dense energy. The next moment, the grid expanded outward faster than any signal, faster than any influence, faster than light. It didn't break the rules, because nothing inside the universe traveled faster than light. The space itself expanded, carrying everything with it. The result of that expansion is the cosmic horizon you learned about a moment ago. Light has had 13.8 billion years to travel, but because of inflation, much of the universe had already expanded far beyond the reach of that light before the first photon even left its home. Most of the universe will never reveal itself to you, not because it is too far away, but because it was born faster than light could ever catch. Inside this early stretching, something else extraordinary happened. Tiny quantum fluctuations, minute ripples at the smallest possible scales, were caught in the expanding fabric and stretched along with it. These were not disturbances in matter. They were disturbances in space-time itself, frozen into place as the universe ballooned outward. Those ripples became the first imprints of structure, the faint wrinkles of creation that seeded every galaxy, every cluster, every cosmic filament stretching across the sky today. You've seen their shadow without realizing it. When you look at the cosmic microwave background, the faintest ancient glow in the universe, you're seeing tiny hot and cold spots. Temperature variations only a few millionths of a degree different. Those spots are the fingerprints of inflation. Each one marks a place where a quantum ripple once existed, expanded to scales billions of times larger, and eventually collapsed under gravity to form the great cosmic web. Inflation didn't just shape the seeds of galaxies. It also solved problems that puzzled astronomers for decades. Without inflation, the universe would look very different from one region to another, but everywhere you point a telescope, you see nearly the same temperature, the same large-scale structure, the same smoothness. Why? Because inflation stretched out the early universe so rapidly that regions which once touched were pulled far apart. They began with the same conditions because they once were the same place. Inflation explains why your night sky looks so uniform, no matter where you turn. It also explains why space appears so flat. If you inflate something enough, like a balloon, you can stand on a small patch of it and not notice the curve. Inflation took whatever shape the universe originally had and stretched it so immensely that any curvature became impossible to detect across the small region you can observe. It flattened the cosmos. It gave it the geometry you measure today. Stephen Hawking once said, "Inflation is the ultimate free lunch." And in a way, it is. Energy poured from the vacuum into expansion. And that expansion built the universe, you know. Inflation gave you galaxies. It gave you stars. It gave you a place to stand in a cosmos that might otherwise have been chaotic and broken. But there is one more idea tucked quietly inside this story, an idea that changes everything. Because inflation ended, but it might not have ended everywhere. The energy field that drove inflation may have settled into a stable state in your region of space, allowing your universe to cool and form atoms. But in other regions, inflation may still be happening. It may never have stopped. Pockets of space could still be ballooning outward faster than light, producing new bubble-like regions with their own physics, their own structures, their own timelines. Your universe might be one bubble among many. This is not science fiction. It is a natural consequence of the equations, of the same mathematics that describe the earliest fraction of a second in your universe. If inflation didn't end everywhere at once, then space would be divided into regions. Some where inflation has ended, like yours, and some where it continues endlessly, forming new universes like sparks from an eternal fire. And if that is true, then the universe you see, the one wrapped inside your cosmic horizon, is only a tiny fragment of something far larger, a single island in a rising sea of possibilities. If inflation happened, most of the universe is forever beyond your reach. Not because it is distant, not because it is hidden, but because it was born faster than light could ever travel. And what inflation leaves behind may be even stranger. Other universes sealed away in their own expanding pockets, each with its own version of reality. The universe didn't explode, it stretched. And in stretching, it may have multiplied. If inflation didn't end everywhere, then your universe might not be alone. When you follow inflation to its natural conclusion, you reach an idea that feels almost too large to hold in your mind, yet too simple to ignore. If space really stretched faster than light during those first fractions of a second, then different regions of it could have cooled and settled at different times. Some regions stopped inflating early, forming universes like yours. Others kept inflating, expanding endlessly. The result is something called eternal inflation, a process that never finishes, never slows, and never stops generating new pockets of reality. You can imagine it as a strange kind of cosmic foam. Not a smooth, even surface, but a froth of expanding bubbles, each separated by vast regions of space that are still stretching faster than light. Inside every bubble is a universe with its own beginning, its own timeline, and its own laws. Outside each bubble is a sea of inflating space that grows too quickly for anything inside to ever escape. Once a bubble forms, it becomes a tiny island in an endless storm. The image that often comes to mind is simple and vivid: bubbles forming in boiling water. Some bubbles appear early others later. Some grow large, others pop quickly. But in the multiverse picture, the bubbles don't pop. They expand. And the water, the energy field driving inflation, keeps boiling forever, creating new bubbles endlessly. Your universe is one of those bubbles. It isn't the center of creation. It isn't the only story. It's one drop in a vast ocean of possibilities. Inside your bubble, the laws of physics look familiar. The forces that govern atoms, the speed of light, the structure of particles. All of these work together to build stars, galaxies, planets, oceans, life, and you. But in another bubble, those laws might not match. The strength of gravity could be different. The types of particles could change. Chemistry might not work the way you know it. In some bubbles, the conditions might be too extreme for atoms to form. In others, stars might ignite instantly or never ignite at all. Some universes may have no time as you recognize it. No stable matter, no light, no possibility of life or structure. Nature tries every combination, filling the cosmic foam with variations, most sterile, a few elegant, and perhaps one or two capable of becoming as rich as yours. This is not a fantasy, and it is not a story invented for entertainment. It is the unavoidable consequence of the same mathematics that describes the earliest moments of your universe. If inflation happened, and if it continued elsewhere after ending in your region, then bubbles would naturally form, each isolated forever from the others. No bridge connects them. No message passes between them. No light crosses the distance. The space between bubbles expands so quickly that nothing inside one universe can ever reach into another. Every bubble is completely sealed off, self-contained, private, and alone. Yet you are not meant to feel alarmed by this. If anything, the idea should feel strangely comforting, because it means your universe is not flawed. It is simply one version of reality among many. The reason it supports stars and planets and life is not because it was destined to. It is because, in the vast range of possibilities, this particular bubble had the right conditions to unfold in a way that allowed complexity to grow. You exist here because you can exist here. This idea is sometimes called the anthropic principle. It doesn't mean the universe was made for you. It means that among countless bubbles, you naturally find yourself in the one where the laws of physics allow observers to arise. It is a quiet, gentle reminder that your universe is not privileged. It is simply compatible with your existence. And even though the multiverse sounds strange, it doesn't change anything about your daily life. The sun still rises. The moon still pulls the tides. The seasons still turn. The sky you see every night is still the only sky you will ever interact with. The idea of other universes doesn't take anything away from yours. It simply expands your sense of scale. It reminds you that even in a cosmos as immense as the one you can observe, there may be far more beyond, hidden by the very nature of reality. You can picture the entire scene from above. Countless bubbles drifting in an endless dark sea, each glowing faintly with its own version of physics, its own unfolding story. Your universe is one of them, floating quietly, expanding softly, held together by laws that allow stars to burn and galaxies to rotate. Somewhere far beyond your cosmic horizon, beyond every galaxy you can see, another bubble may be forming right now, faster than any light could ever travel, sealed off forever by the inflating space between you and it. Max Tegmark once said, "Our universe is not just huge, it's possibly part of a much bigger multiverse." If he is right, then everything you know is part of something much larger, a structure you cannot touch but can imagine, a pattern woven into space-time itself. And even if there are other universes, yours still has mysteries of its own. Inside your cosmic bubble, space may hold secrets you have not yet seen. Shapes within shapes, patterns hidden behind the horizon, paths that might loop back on themselves without you ever realizing it. And inside your own universe, the shape of space still carries its own mysteries. As you drift farther into the structure of the universe, another question rises quietly beneath the surface of everything you've explored so far. If your universe is one bubble in a cosmic sea, then what is the shape of the bubble itself? Not the shape of galaxies or clusters or filaments, but the shape of space, the geometry of the invisible framework that holds everything. It turns out that space can take on only 3 possible large-scale shapes, each one deeply tied to how the universe expands, how gravity works, and even how the cosmos might someday end. These shapes don't reveal themselves through simple observation. You can't look up at the sky and see curvature the way you'd see the curve of Earth from an airplane window. Instead, you understand them through the way light moves, the way distances add, and the way the earliest glow of the universe, the cosmic microwave background, spreads across the sky. The first possibility is a flat universe. In a perfectly flat cosmos, Euclid still rules. Triangles add up to 180 degrees. Parallel lines never meet. Light travels in straight paths that don't bend unless matter or energy is present. This is the geometry you learned in school. The geometry that feels normal to your daily life. A flat universe can expand forever without curving back on itself, and it suggests a cosmos whose structure is surprisingly simple at the largest scales. The second possibility is a closed universe. In a closed geometry, space curves back upon itself like the surface of a sphere. Triangles have angles that add up to more than 180 degrees. Lines that start parallel eventually meet. If you could travel in a straight line long enough, and if the universe stayed static, which it won't, you could eventually circle around and return from behind yourself without ever turning. It's a strange, looping geometry, one that makes the universe finite in volume, but without any boundaries. There is no edge, no wall, no cliff. Space curves smoothly back into itself. The third possibility is an open universe. In this geometry, space curves outward like a saddle. Triangles have angles adding up to less than 180 degrees. Distances grow faster than intuition expects. Parallel lines diverge. A universe with this shape expands forever, its curvature gradually stretching space apart more and more as time goes on. This cosmic geometry feels airy and vast, a kind of ever-unfolding openness. So which shape does your universe have? To answer that, astronomers turn to the oldest light you can see, the CMB. When you map this faint glow across the sky, the size of the subtle hot-cold patches acts like a ruler. In a curved universe, those patches would appear distorted or stretched. But the patterns are remarkably undistorted, suggesting that space is extremely close to flat. But here's the subtlety. Nearly flat is not the same as perfectly flat. Astronomers can only measure the curvature within the observable universe. which is itself limited by the cosmic horizon. If the universe is much larger than what you can see, and inflation strongly suggests it is, then even a curved space would appear flat to you, just as a tiny insect walking on a massive balloon might believe it is moving on a perfectly flat plane. Inflation smoothed out whatever initial curvature the universe might have had, stretching space to such enormous scales that your visible region looks uniform and level. This is why the shape of the universe is not just a matter of geometry, it is a matter of scale. If the universe is flat, it may expand forever. If it is closed, it might someday slow, stop, and curve inward again. If it is open, its expansion will continue accelerating. The shape is tied to destiny. It reveals the long-term fate of everything you know. And yet even that isn't the full story, because shape is not everything. Two universes can be flat, but behave completely differently if their topology, the way space is connected, differs. You can imagine a universe that is flat but finite, like a three-dimensional version of a donut, where traveling straight eventually loops you back around. Or a universe with hidden twists, folds, or tunnels that change how distances wrap around themselves, even when the geometry looks ordinary. This is where your imagination starts to drift beyond simple geometry, because the universe might not just bend. It might connect. It might wrap around. It might loop in ways you don't intuitively sense, ways that don't reveal themselves until you think about space as something flexible, something with structure deeper than measurement. Neil deGrasse Tyson once remarked, "The universe is under no obligation to make sense to you." And nowhere is that more apparent than in the shape of space itself. You live in a cosmos where triangles behave normally, where distances add predictably, where the sky looks smooth and flat. But just beyond your perception, the universe may curve subtly. It may hide a deeper structure. It may loop back on itself or stretch into forms no one has yet imagined. And that brings you to the next question, the one that pushes you a little further from comfort into wonder. If space has a shape, can it also have a path? Can it connect in ways that let you leave one point and arrive back where you started without ever making a turn? So let's ask a deeper question. What if space loops? When you think about the shape of the universe, you picture something smooth and continuous, a sphere, a flat expanse, or a gentle saddle. But shape is only half the story. The deeper question, the stranger question, is how space connects to itself. This hidden structure is called topology, and it tells you whether the universe, no matter what shape it has, might secretly loop, twist, or fold in ways that your senses cannot detect. Topology is not about angles or curvature. It is about connections. Two objects can look completely different, yet share the same underlying structure, as long as the pathways through them match. The classic comparison is a donut and a coffee mug. One has a circular hole, the other has a handle. They look nothing alike, yet in the language of topology, they are the same because they both contain exactly one hole. You can stretch, bend, twist, or deform one into the other without cutting or tearing. The number of holes stays the same, and that number defines the topology. Now apply that idea to the three-dimensional space you live in. Even if the universe is flat, like an infinite sheet, its topology might still be far more complicated. One possibility is a three torus, a shape that's hard to visualize but not hard to describe. Imagine that space wraps around itself in all three directions. If you travel far enough in a straight line, you eventually return to the point you started. Not because you turned, but because the path loops. There are no walls, no edges, no boundaries. The universe feels infinite, yet it is connected like the surface of a torus, looping endlessly in every direction. If the universe had this topology, strange consequences would follow. Light traveling across space could loop around the cosmos, creating ghost copies of galaxies or even ghost copies of your own region. In principle, you might look deep into the night sky and see a distant version of the Milky Way, not because it is far away, but because the light from your galaxy wrapped around the universe and returned from the other side. You could look forward and see something that sits behind you. The universe would become a subtle hall of mirrors, reflecting patterns across its structure without any physical mirrors at all. But here's the catch. The universe appears to be too young for light to have completed a full loop, assuming the topology is large. Even if space does wrap around itself, the size of the loop might be far bigger than the part of the universe you can currently observe. If the universe is smaller than your cosmic horizon, you would see repeating circles or patterns in the CMB, echoes of the same regions from different angles. Astronomers have searched carefully for these repeating signatures in the sky. So far, none have been found, which tells you two things. Either the universe is not a looped space, or if it is, the loops are far larger than the sphere of visibility you inhabit. This does not rule out the possibility of a connected universe. It simply means your cosmic bubble is too small to reveal the full structure. You might be living in a space far larger than your horizon, a space with hidden pathways that only light traveling billions of additional years could uncover. Until that light arrives, which it may never do, the loops remain silent. You can imagine yourself walking inside a vast hall of mirrors, where the mirrors are so far apart that you never reach them. You feel the openness and see nothing unusual, but somewhere beyond your reach, the reflections wait. The universe might be finite, but impossible to sense. It might be looping quietly around you without leaving any visible trace. You live in a cosmos that could be deeply interconnected while appearing perfectly ordinary from your limited viewpoint. There's a gentle beauty in this idea, a universe that is both intimate and immense, a universe that feels infinite but may fold back on itself in the most subtle ways, a universe that hides its deeper structure not out of malice, but because time has not yet allowed you to see far enough. And there is another reason you haven't seen ghost copies of galaxies. The universe is expanding. Light is stretched. Distances grow. Even if space loops, the expansion may prevent any signal from ever completing the journey. By the time it returns, space itself may have grown too large for the loop to matter. You might already be seeing copies of distant galaxies, but the universe is too young for their light to return. Still, the possibility remains. Topology reminds you that space can be far stranger than your instincts suggest. Even an infinite universe can have finite topology. The shape you measure is only the local geometry. The deeper truth lies in the connections, how one region links to another, how paths wrap around the whole. how space might fold into a coherent whole. John 11 once said, "If the universe is finite and small, we might one day see the back of our own head made of starlight." It's a humorous thought, but also a profound one. It captures the strange blend of humility and wonder that cosmology invites. You live in a universe where space might be looping, hiding pathways that only the future could reveal. And if space can loop, then light might loop too. Its journey could take it in circles so vast that no human era will last long enough to see the full pattern. That is the quiet mystery of cosmic topology, a structure you cannot touch but can imagine, a geometry you cannot map but can sense in the possibilities. But before you talk about copies of galaxies or repeating patterns written across the sky, you have to understand the oldest image the universe has ever left for you. When you look out into the universe, you are not just seeing distance. You are seeing time unspool behind you, layer by layer, like pages in an ancient book. But eventually, if you look far enough, you reach a page that refuses to turn. A page written so early in the story of the cosmos that no light from before it can ever reach you. That page is the cosmic microwave background, the CMB, and it is the oldest light you will ever see. To understand what the CMB is, imagine the universe in its earliest childhood. Not quiet, not gentle, but roaring with heat. In those first hundreds of thousands of years, everything was so dense and so hot that atoms could not exist. Electrons and protons were free particles drifting in a thick plasma, scattering light constantly. Photons bounced around as if trapped inside an endless fog, colliding over and over again, never traveling more than a tiny fraction of an inch before being absorbed and re-emitted. The universe was glowing, but nothing in that glow could escape. Light existed, but it was imprisoned. Then, something calm happened, something transformative. As the universe expanded, it cooled, and at around 380,000 years old, still a newborn by cosmic standards, its temperature fell low enough for electrons to join with protons and form neutral atoms. Suddenly, light was no longer pinned down. Photons that had been bouncing endlessly through the plasma were released, free to travel across space for the first time. That release created a flash, not a sudden burst like lightning, but a universal sigh of radiation expanding outward in every direction. That ancient light is still reaching you today, stretched by 13.8 billion years of cosmic expansion. Its wavelength has been lengthened from scorching visible light into soft microwaves. It has faded, cooled, and dimmed, but it endures. It fills the universe like a thin, perfect mist of energy. When you tune a radio to static, a tiny fraction of that hiss is the sound of the universe's first light brushing against your antenna. This is why astronomers call the CMB a baby picture of the universe. It is the earliest photograph you can ever see, a portrait taken long before galaxies formed, long before stars lit up the darkness, long before any structure took shape. Look at the CMB, and you are looking at the universe when it was barely learning to breathe. But that picture is not perfectly smooth. It is almost perfectly smooth, far smoother than any random process should allow. But scattered across it are tiny hot and cold spots, variations only a few millionths of a degree different from each other. And those spots matter. They are the fingerprints of inflation, the stretched out wrinkles of quantum fluctuations. They are the seeds from which all galaxies, all clusters, all cosmic filaments eventually formed. Every star you have ever seen grew from one of those faint ripples. Every cosmic pattern began as a tiny temperature difference frozen into place in that first light. The CMB also holds clues about the geometry of space. The size of its hot and cold patches acts as a ruler, revealing curvature, density, and the overall structure of the cosmos. It is not just a picture, it is a map drawn by light older than any star, older than any galaxy, older than any metal or molecule or planet. And yet, as beautiful as it is, the CMB is also a boundary. You cannot see past it with light. Before atoms formed, the universe was opaque. Light could not cross it. No telescope, no future instrument, no matter how powerful, can look back beyond that moment using photons. The CMB is the second great wall of the universe, a wall made not of matter or gravity, but of transparency. On one side of the wall, the universe sends you messages. On the other side, silence. But the silence is not absolute. While photons were trapped in the early plasma, other messengers were not. Neutrinos, tiny ghost-like particles, streamed freely from the earliest moments, barely interacting with anything. They carry whispers of an even deeper past, a cosmic neutrino background that predates the CMB by hundreds of thousands of years. And beyond neutrinos, gravitational waves, ripples in space-time itself, could carry information from the very birth of the universe, potentially even from the instant of inflation. You cannot yet see those signals directly, but the possibility remains, humming beneath scientific curiosity. The idea that light is not the only storyteller in the cosmos. For now, the CMB is your horizon of sight. It is the last surface from which light can reach you. It surrounds you like a fragile shell, about 46 billion light-years away in every direction, marking the limit of what photons can reveal. When you look at it, you are looking at the universe's childhood. When you study its patterns, you are reading the earliest chapter of everything. George Smoot, one of the scientists who first mapped the CMB with precision, once said, "If you're religious, this is like seeing the face of God." And standing on your quiet evening, listening to the soft drift of cosmic history, you might feel a touch of that awe, the sacredness of touching something impossibly old, impossibly distant, impossibly fragile. This is the oldest light you will ever see, and it marks the second wall of the universe. But even though you cannot look beyond the CMB with photons, you can still measure what lies across the cosmos. You can still trace distances, map structures, and build a ladder to climb farther into understanding. But how do we measure something so vast? We build a ladder. When you look up at the night sky, every star and galaxy seems close enough to touch. They sit on a flat canvas, scattered like bright grains of salt on black velvet. But that is an illusion. The universe is three-dimensional, expanding, and vast beyond comparison. You can't fly to a distant galaxy. You can't drop a measuring tape between two clusters. You can't walk across light years or step across millions of parsecs. So how do you measure something you can never reach? Astronomers solve this problem with a creation both humble and ingenious, the cosmic distance ladder. It is not a physical structure. It is a chain of methods, each one built on the one below it, each extending your reach a little farther into the dark. It is how you measure the unmeasurable. The first rung of the ladder is parallax, the simplest and most direct way to measure distance in the sky. As Earth orbits the Sun, your view of nearby stars shifts slightly. The way a foreground tree seems to move against the background mountains as you walk past it. By measuring the tiny change in angle between two opposite points in Earth's orbit, 6 months apart, you can calculate how far away a star is. For the closest stars, this works beautifully. But beyond a few thousand light years, the angles become too small to detect. Parallax gives you your first foothold, but not more. To climb higher, you need a new kind of ruler, one that shines with predictable power. The second rung is built from Cepheid variable stars. These stars rhythmically brighten and dim over precise intervals, and the length of their cycle tells you how bright they truly are. Compare their true brightness with how faint they appear from Earth, and you have their distance. Cepheids are strong candles, visible across millions of light years. They carry you from nearby stars to nearby galaxies, bridging the gap that parallax cannot cross. But space is larger still, and you need an even brighter beacon. That brings you to the third rung, type Ia supernovae. These explosions occur when white dwarfs reach a critical mass and collapse into fire. Because they all ignite at nearly the same mass, they all reach nearly the same peak brightness. They are so luminous that they can outshine entire galaxies. A single supernova can be visible from billions of light years away. These events revealed one of the most important discoveries in modern cosmology, that the universe is not just expanding, but accelerating. The fourth rung of the ladder is not based on brightness at all. It is based on motion. As the universe expands, light from distant galaxies is stretched, shifting toward the red end of the spectrum. This redshift tells you how fast a galaxy is receding from you. Combined with what you know from supernovae and Cepheids, redshift lets you estimate distance across vast stretches of space. It is not a direct measurement, but a relationship, a connection between how the universe grows and how the light changes. Then you reach the fifth rung, BAO, or baryon acoustic oscillations. These are ripples frozen in the large-scale structure of the universe, imprinted by sound waves that traveled through the early plasma before the CMB was released. These ripples set a standard cosmic length, an enormous ruler etched into the positions of galaxies. By measuring how this cosmic scale appears at different distances, you can map the universe's expansion across time. BAO is subtle, elegant, and powerful. It anchors the farthest reaches of the cosmic distance ladder. All these methods together allow you to measure the universe. But the ladder has a peculiar property. Each rung depends on the ones before it. A small error in the first rung grows larger in the next. A difference in calibration echoes across the entire chain. This is why cosmologists sometimes find themselves in disagreement. Two different ways of measuring the expansion rate of the universe, using nearby Cepheids and supernovae on one hand, and CMB and BAO data on the other, give two different answers. This tension, known simply as the Hubble tension, hints that something might be incomplete in our understanding, or that the universe holds a subtle clue still waiting to be uncovered. Measuring the cosmos is like trying to measure the waves on a shoreline while the tide is moving beneath you. Your rulers stretch as you measure, The distances shift while you calculate them. Light changes as it travels. Space evolves. The universe is not a static object on a table. It is a living landscape whose dimensions change with time. And yet, through all this complexity, the distance ladder works. It reveals structures billions of light years away. It confirms the fingerprints of inflation. It maps the cosmic web. It gives you a sense of scale in a universe too vast for human intuition. Edwin Hubble once said, "Equipped with his 5 senses, man explores the universe around him and calls the adventure science." That feeling, the quiet adventure, the calm determination, the respect for the craft, is at the heart of the distance ladder. It is not about perfection. It is about understanding. It is about reaching a little farther today than you could yesterday. This is your moment to breathe, to rest, to absorb the subtle elegance of measuring something impossibly large. Because the next step in your journey is stranger. If distance is measured through light, and light travels through expanding space, then what if the very concept of distance is not fixed, but shifting? As you move deeper into the structure of the cosmos, the very idea of distance, something that feels so simple on Earth, begins to blur and stretch. In your everyday life, distance is fixed. A mile is a mile. A foot is a foot. But in a universe where space itself expands, distance becomes something fluid, something dynamic, something that depends on how you choose to measure it. Astronomers use several different definitions of distance, not because they enjoy complexity, but because each definition answers a different question. The first is co-moving distance. This is the distance between 2 points in the universe if you remove the expansion of space from the equation. Think of it as a coordinate grid laid across the cosmos, where every galaxy sits on a dot. As the universe expands, the grid stretches, but the dots stay fixed. Co-moving distance tells you where things are in a timeless map. Then there is proper distance, which is what you would measure if you could freeze the expansion of the universe at a single moment and stretch a cosmic ruler between 2 galaxies. Proper distance changes with time, because space itself changes with time. If the universe expands, proper distance increases, even if the galaxies never move through space at all. And finally, there is light travel distance, which is simply how long it takes light to cross the gap. When you see a galaxy 10 billion light years away, that means its light spent 10 billion years traveling. But because the universe was expanding during that time, the actual proper distance between you and that galaxy now is much larger. In an expanding universe, these 3 distances, co-moving, proper, and light travel, are not the same. They diverge. They disagree. They tell you different truths about the same stretch of space. There is another kind of distance that bends intuition even further. Angular diameter distance. This one tells you how large an object appears based on its angular size in the sky. But here's the twist. In an expanding universe, an object can actually look larger the farther away it is, up to a point. This happens because when you look very far into the past, you see the universe when it was smaller, when galaxies were closer together. Their light began its journey when distances were compressed. So sometimes a galaxy 10 billion light years away appears bigger than one 5 billion light years away. Space is not just big. It is shifting under your feet. This is why measuring distance in cosmology can feel like measuring something drawn on a balloon while the balloon is being inflated. 2 points on the balloon can drift farther apart without either point moving across the surface. The increase in distance is not motion, it is expansion. This leads to another strange truth. In an expanding universe, galaxies can recede from you faster than the speed of light. This does not violate relativity because nothing is traveling through space faster than light. Instead, the space between you and the galaxy is expanding faster than light. The rules hold. The universe simply grows. This also affects how light travels. Photons follow curved paths, called geodesics, through expanding spacetime. As they move toward you, the space they cross stretches, pulling the light itself into longer wavelengths. This is why distant galaxies are redshifted. Their light is literally stretched by the growth of space. And here is the quiet astonishment. Light that is coming toward you right now may never reach you. If the space between you and a galaxy expands faster than the photon can cross it, the photon will forever chase a target that outruns it. There are galaxies whose light is on the way, but the accelerating universe will stretch the space so rapidly that the photons will fall farther behind over time. They will never arrive. This reveals a cosmic loneliness built into the fabric of the universe. As expansion accelerates, more and more galaxies slip beyond reach. They don't vanish. They don't dim instantly. Instead, their light is stretched until it fades into infrared, then microwaves, then wavelengths too long for any detector to capture. One by one, they drop behind the cosmic horizon. If you wait long enough, trillions of years, the universe will become a quieter place. The night sky will hold fewer galaxies, then only a handful, then perhaps none at all. The cosmos will expand so fast that the observable universe will shrink to a small island of what once was a vast expanse. The idea is calm but weighty. Distance is not a fixed idea. It is a changing property of reality. When space expands, distance bends. When the universe accelerates, distance stretches. When you look at the cosmos, you are not seeing a static landscape. You are watching a living structure grow and shift beneath the light. Brian Greene put it clearly. Space itself can expand faster than light. That single sentence reshapes how you think about the universe. It means distance is not simply a number. It is a relationship between light, time, and expansion. And as space grows, something else fades away, our future sky. So what does this mean for the universe we will see in the far future? As you listen and breathe slowly, you may feel the universe expanding around you, not with sound or motion, but with the quiet knowledge that space is growing, stretching, drifting outward in all directions. And with that growth comes a truth that is both beautiful and bittersweet. The universe you see tonight is not the universe your distant descendants will see. Over time, the cosmos will slip away piece by piece, like a shoreline fading into fog. To understand this, you must return to the idea of horizons, not the cosmic horizon of what you can see now, but the future horizon, the boundary of what you will ever be able to see. As the expansion of the universe accelerates, more and more galaxies are carried outward faster than their light can ever travel back toward us. These galaxies aren't moving through space. Space itself is growing between us and them, stretching their light until it becomes invisible. Right now, you live in a fortunate era. The night sky still holds thousands of galaxies you can detect with powerful telescopes. You can see across cosmic time. You can watch light that began its journey when Earth had no oceans, no continents, no life. You can observe the universe as it was in its fiery youth. But that window is temporary. The acceleration of space means that much of what you see today is already slipping away. In the far future, the universe will look very different. Closer to home, the Milky Way will not disappear. Instead, it will merge with its nearest large neighbor, the Andromeda Galaxy. Their mutual gravity is slowly pulling them together, and in about 4 billion years, their stars will swirl into a single, enormous elliptical galaxy, a new structure astronomers call Milkdromeda. It will be a glittering island of hundreds of billions of stars, rotating slowly in the dark. But nearly all other galaxies, even those we see clearly today, will fade from view. They will not simply dim. They will cross the future horizon. Their light will be stretched beyond visibility, beyond detectability, beyond the domain of any possible telescope. Eventually, the only galaxy visible to future observers will be Milkdromeda. The cosmic web, the grand structure of clusters and filaments, will vanish from the night sky. Imagine an astronomer living trillions of years from now. They will look upward and see a silent sky with one single galaxy in it. They will search for signs of expansion, but they will find none. They will try to detect the CMB, but it will be stretched into wavelengths so long, so cold, that no sensor could capture it. The signature of the Big Bang will be gone. For them, the universe will appear static, timeless, eternal. They may conclude that their galaxy is the entire cosmos. They may think the universe was always like this, dark, quiet, lonely. The universe will forget its own origin. Lawrence Krauss once remarked, "In the far future, the universe will be dark, cold, and empty." This is not a warning. It is simply the natural consequence of expansion. Over unimaginable timescales, stars will burn out one by one. Galaxies will drift apart. The glow of starlight will fade, like embers at the end of a campfire drifting into darkness. Even the atoms themselves will grow sparse as space expands. The cosmos will become quiet, and yet there is a gentle beauty in this solitude. The night sky will soften, dim, and become calm. The noise of creation will fade. The universe will settle into a long, slow exhale. For you, living now, there is a kind of privilege in this moment. You are alive at a time when the universe is still bright, before its stories drift out of reach. You can see the evidence of the Big Bang. You can measure the cosmic expansion. You can observe distant galaxies that future civilizations will never know existed. You live in a rare window when the cosmos is both old enough to reveal its past and young enough to remain visible. That is a quiet gift, a fleeting clarity in cosmic history. The future sky will go dark, but your moment is bright. Your vantage point is special. You stand between the ancient glow of the CMB behind you and the slow dimming of the universe ahead of you. You are here during the brief era when the universe can still speak, when its farthest edges still whisper their secrets. And as you breathe gently, you may feel a calm sadness mixed with wonder, a recognition that nothing lasts forever, not even the light of galaxies. But there is peace in that too. The universe does not end abruptly. It simply becomes quieter over time, like a story softening into silence. And yet, even emptiness has an edge worth exploring. When most people imagine the universe, they picture it as a giant container, something with an inside, something that might, at some unimaginable distance, have an outside, a place where everything stops, a place where beyond the last star, beyond the last atom, there might be something or nothing. Cosmologists, though, rarely think this way. Almost none believe the universe has a physical edge, a wall, a boundary, a cliff where space simply stops. Every observation you can make shows the same thing. No matter where you look, space continues smoothly. There is no thinning, no fading, no sign of a boundary where physics breaks. Space does not behave like the surface of a planet you can walk to the edge of. It is not a platform floating in something larger. It is the something larger. And yet, it can be helpful, even comforting, to imagine what an edge could feel like. Not as a prediction, but as a thought experiment, an exploration of how your mind grapples with the infinite. So imagine that you begin to walk. You head outward in a straight line, past the nearest stars, past the halo of the Milky Way, past the faint glow of distant clusters. As you travel, light around you stretches into deeper reds, then into darkness. The expansion of space becomes more noticeable. Time itself begins to shift, stretching differently for you and for those you left behind. You feel no wind, no resistance, only a soft thinning, as if the fabric of space-time itself is becoming delicate under your feet. You walk across a thinning fabric of space-time. In this dreamlike journey, suppose you keep walking until you reach what you imagine to be the edge. You would not find a wall. You would not find a void waiting to swallow you. You would not find darkness, or silence, or emptiness in the way you expect. At a true edge, if it existed, you would find something far stranger, the absence of anything at all, even space, even time, even the possibility of existence. Edges in cosmology are not like edges in the physical world. They are like the boundaries of mathematical manifolds, limits where the coordinates stop making sense. A boundary, in this abstract sense, is not a thing you encounter. It is a place where the rules that allow place to exist simply fade away. You could not stand at such a boundary. You could not look beyond it. Beyond would not exist. Even the idea of turning around would fail, because orientation itself relies on the geometry of space. And at the boundary, that geometry ends, not abruptly, but conceptually. Thought experiments about an edge reveal more about our human instincts than about the cosmos. We are creatures who dislike infinity. We crave closure, a circle, a boundary, a destination, something to lean against, something that tells us where the world stops. Our brains evolved on finite landscapes, caves, forests, coastlines, and so we try to impose those shapes on the universe. But every observation tells us that space continues, in all directions, with no thinning, no fading, no hint of an approaching edge. The universe does not behave like something that stops. It behaves like something that simply is. Still, the idea of edges does appear elsewhere in cosmology. In multiverse models, different bubble universes may be separated by boundaries, not physical ones, but transitions in the underlying fields of reality. These boundaries are not walls. They are regions where the laws of physics shift from one form to another. But even those cannot be crossed, because crossing them is not like walking across a field. It is like trying to walk into a different definition of existence. What stops you is not matter. What stops you is meaning. An edge of the universe wouldn't be a wall. It would be the absence of everything, even spacetime. This subtle idea does not make the universe smaller. It makes it stranger, more dreamlike. The universe doesn't end where space ends. It ends where definitions fail, where the framework that allows concepts like position, motion, direction, and distance no longer applies. So what does an edge really mean? Not a place, not a structure, but a question, a limit of imagination, a boundary your thoughts can touch, even if you can never walk there. Sean Carroll once wrote, "Infinity is not a place, it's a limit of our descriptions." And in this moment, drifting through a quiet night, you can feel that truth. The universe is not a container. It has no rim, no outside, only layers of understanding, some of which flatten into silence when pushed too far. But even without an edge, some dreams try to escape our cosmic prison. For as long as humans have looked into the night sky, there has been a quiet longing beneath every question. Could we ever go there? The stars are beautiful, but they are far, too far. Even the nearest star is 4 light years away, and our fastest spacecraft would need tens of thousands of years to reach it. And when you hear that nothing with mass can travel faster than the speed of light, it can feel like a door closing. A gentle, cosmic no. But the universe rarely speaks in absolutes. It often whispers something softer, something more intriguing. Not that way, but maybe another. Because the rule is not that nothing can outrun light. The rule is that nothing can move through space faster than light. Space-time itself, however, its geometry, its curvature, its structure, plays by different rules. And that is where imagination meets physics. The first idea is the warp drive, built from a solution to Einstein's equations known as the Alcubierre metric. In this concept, the ship does not move at all. Instead, space in front of the ship contracts, and space behind it expands. The ship sits inside a bubble of calm space-time while the universe around it shifts. You're not speeding through space. The space itself is rearranging. It's like surfing on a moving wave, or like standing still while the road rolls beneath you. The speed limit remains unbroken because the ship never exceeds the speed of light locally. But the distance between two places changes. Warp doesn't break the speed limit. It moves the road. The mathematics works. Einstein's equations allow it. But there's a catch. Generating this bubble requires exotic matter, something with negative energy density, the opposite of anything we know how to create in large quantities. Small amounts of negative energy appear in quantum physics, but nothing close to what a warp drive would need. So the idea remains possible, but not practical, not yet. Then there are wormholes, tunnels through space-time that act like shortcuts. Instead of traveling across the fabric, you slip through a folded layer, emerging somewhere else instantly. In diagrams, wormholes look simple, 2 mouths connected by a throat. But maintaining such a tunnel requires negative energy as well, enough to prevent the wormhole from collapsing faster than anything could pass through it. Kip Thorne once said, "Wormholes are permissible by the laws of physics." but they may be impossible to create. It's a sentence that perfectly captures the quiet contradiction of faster-than-light dreams. Allowed in theory, forbidden in practice. And even if you could stabilize a wormhole or power a warp bubble, you would run headfirst into another set of problems: time loops and causality paradoxes. A wormhole linking two different times could allow you to form a closed time-like curve, a path through space-time that brings you back to your own past. It raises scenarios like the classic grandfather paradox, where cause and effect tangle until logic buckles. Some physicists suspect that the universe protects itself from such violations. Stephen Hawking proposed the chronology protection conjecture, the idea that quantum effects would destabilize any time machine the moment it became dangerous to causality. In this view, the laws of physics allow us to imagine wormholes, allow us to write equations for warp bubbles, allow us to explore what-if scenarios. But reality resists letting them exist. You can think of space-time like a sheet of cloth. If it could bend freely, you could fold two distant points together. Traveling the shortest path might mean traveling through the fold instead of across the surface. But the cloth of the real universe carries tension. It resists certain shapes. It tries to protect the consistency of events. Still, there is a gentle thrill in imagining it. A ship surfing on expanding space-time. A traveler stepping through a tunnel woven from gravity itself. A shortcut where the universe quietly rewrites its geometry. These ideas feel like science fiction, but they rest on the mathematics of general relativity. The universe does not forbid imagination. It invites it, yet it also guards reality. Negative energy remains elusive. Wormholes collapse instantly. Warp bubbles require more energy than exists in the observable universe. And the deeper we explore, the more cautious the cosmos seems. Faster than light travel does not break physics. It breaks our intuition. The universe operates on principles that stretch beyond our everyday sense of distance, speed, and time. And within those principles, you find possibilities that are extraordinary but grounded, beautiful but disciplined. The universe seems to say, dream as far as you like, but the rules remain. And that brings you to an even stranger idea, one where space is no longer the fundamental stage, a place where reality itself dissolves into something more abstract, more subtle, more informational. But what if the deepest truth of the universe is not about space at all? As you drift deeper into the quiet of the night, another idea rises from the edge of physics. Gentle, strange, and almost whispered, it is an idea born not from science fiction, but from the mathematics of gravity, quantum theory, and the mysteries of black holes. It suggests that reality, as you experience it, 3 dimensions of space unfolding around you, may not be the whole story. This idea begins with a puzzle. A black hole, the densest object in the universe, has a property called entropy, a measure of how much information it can contain. Jacob Bekenstein and Stephen Hawking discovered something astonishing. The entropy of a black hole doesn't scale with its volume, the way you would expect if information were stored inside it. Instead, entropy scales with the area of its event horizon, the 2-dimensional surface surrounding it. This simple fact, this small, quiet formula, carries a profound implication. It suggests that everything that falls into a black hole everything it contains, everything that defines it, is encoded not in the three-dimensional space inside, but on the two-dimensional surface outside. A 3D world described by a 2D boundary. That single insight opened a door. If the information inside a black hole can be described by data written on its surface, then perhaps the same is true of the universe itself. Perhaps what you see as three-dimensional reality, space stretching in every direction, galaxies drifting across the cosmos, you sitting here tonight listening, is actually encoded on a distant two-dimensional boundary, not as a trick, not as an illusion, but as a way the universe keeps its information consistent. This is the holographic principle. At its heart, the idea is simple. The world inside is encoded on a surface outside. Three-dimensional reality is a projection of two-dimensional information. Just like a hologram etched into a thin sheet of material can display a full 3D image. When illuminated, the universe you inhabit may be the higher dimensional expression of information stored on a cosmic horizon far away. This doesn't mean the universe is fake. It doesn't imply you are living inside a simulation. It isn't a computer program or a dream. It is a description, a mathematical framework that helps unify gravity, quantum mechanics, and thermodynamics. It is a way of saying that information may be more fundamental than space, more fundamental than matter, more fundamental than the geometry of the cosmos. The holographic idea feels metaphysical, but it is grounded in the deepest physics we have. In string theory and quantum gravity research, some models show that a universe with gravity in 3 dimensions can be equivalent to a universe without gravity in 2 dimensions. 2 descriptions, 1 reality. One written on the surface, the other unfolding inside. Neither less real than the other. Imagine for a moment that every particle, every field, every law of nature is encoded on a faint, distant screen. A cosmic boundary that surrounds everything. You never see this boundary. You never approach it. Yet the information stored there gives rise to everything you experience. The shape of space, the flow of time, the formation of galaxies, the birth of stars, the breath you draw. The universe may not be made of matter and energy, but of information, patterns, relationships, codes. Sitting here, wrapped in the stillness of the night, this idea does not feel frightening. It feels clarifying. So much of the cosmos already behaves like information. Quantum states, entanglement, thermodynamic order. The holographic principle extends that logic to the entire universe, inviting you to imagine reality as something both elegant and fundamentally simple beneath the surface. Leonard Susskind once said, "The world is a hologram." And whether the principle turns out to be literally true or simply a powerful metaphor in physics, it opens your mind to a new kind of wonder. A gentle sense that what you call space is not the final layer of truth, but a doorway into something deeper. To understand beyond the horizon, you might whisper to yourself, we may need to understand the code itself. And now, let's drift toward the quietest place of all. You've traveled far tonight, farther than any ship could take you, farther than light could hope to carry you. And now, as the journey softens and the night settles around you, it's time to drift gently back, to return not with answers, but with a quiet understanding that the questions themselves have a strange and gentle beauty. You began at the cosmic horizon, the shimmering boundary made of time itself, where the light of distant galaxies stretches into silence. From there, you step backward into the first moment of creation, into inflation, when the universe expanded faster than light, stretching tiny quantum ripples into the seeds of galaxies. You drifted outward into a sea of possibilities, where eternal inflation paints the cosmos as a foam of multiverse bubbles, each with its own laws, its own story, its own beginning. You trace the shape of everything, learning how space may be flat, curved, or open, and how even a flat universe can hide deeper connections. Then you slipped into the subtle world of cosmic topology, where space itself may loop, wrap, or fold in ways unseen, where you could travel straight and return from behind yourself, yet never meet an edge. After that, the journey carried you to the oldest light in existence, the cosmic microwave background, a baby picture of the universe glowing softly across space-time. You touched that light with your imagination, feeling its 13.8 billion year journey as if it had been traveling just for you. From there, you stepped onto the cosmic distance ladder, understanding how astronomers measure the immeasurable using parallax, pulsating stars, supernovae, and the stretched-out fingerprints of the early universe. You learned how distance itself becomes a fluid idea when space expands. Then came a softer sadness, the story of the future universe, where distant galaxies fade past the horizon, where the sky grows empty, and where the universe forgets its own origin. A truth that is beautiful, quiet, and deeply human. You wandered into dreams of warps and wormholes, where space-time might fold, creating shortcuts and tunnels, not forbidden by physics, only protected by reality. And you felt the gentle thrill of possibility, grounded in calm understanding. Finally, you stepped into the deepest layer, the holographic universe, where the world you live in could be a three-dimensional expression of information encoded on a distant surface, where the universe becomes a whisper of data and matter becomes meaning. Through it all, one truth followed you like a soft companion. No one knows what lies on the other side of the universe. Not scientists, not philosophers, not dreamers, not even the universe itself, perhaps. And that not knowing is part of the wonder. You are floating tonight inside a warm bubble of light, wrapped gently in time. Your entire observable universe, a sphere of nearly 92 billion light years, rests around you like a silent shell, filled with stories written in photons. You may never know what lies beyond it, but the universe does not need to be complete for you to feel at home within it. You are living in the golden age of cosmic observation, a fleeting moment when the universe is still bright enough to reveal its beginnings, yet old enough to share its deepest clues. Billions of years ago, this view was impossible. Billions of years from now, it will fade. But you, right now, are here at exactly the moment when the cosmos is telling its story clearly. And as that story settles into you, let the pace slow. Let your breath soften. Let the universe grow quiet around you. You are safe. The universe is quiet tonight. You don't need to understand everything. You don't need to chase every horizon. You don't need to hold the entire cosmos in your hands. Wonder is enough. The questions are enough. The mystery is enough. Because what lies on the other side of the universe may not be a place. It may be a feeling, a moment of stillness, a sense of belonging in something infinitely large. Somewhere, something incredible is waiting to be known. Carl Sagan's words drift softly here, like a final lantern glowing above the dark. Tonight, you can let the universe rest. Let your thoughts settle like stardust. Let your breath fall into rhythm with the quiet expansion of space. You are safe in your small corner of an endless sea, held gently by time, cradled by the strange, beautiful cosmos that made you. And so this journey ends not with certainty, but with peace. Not with answers, but with wonder. Good night, traveler. And may the universe be gentle with your dreams.